Hi, folks. Dr. Cole here. We're going to move on to the next part of the course. And in this part of the course, we're going to be working with a new software called JASP. So I posted all the lectures in a Google Drive folder, and then you'll be working from that folder, grabbing the assignments from Canvas, submitting your work in Canvas. All right, so let me share the screen. Let's get going here. Okay, so here's that Google Drive folder called JASP. JASP is new software that's built on R. So the first lecture that we're starting in our JASP learning is the t-test. Let's get into that folder, and we're going to start here. This is our lecture. And the video link, when I'm done recording, it will be here. Let's go ahead and make this a little bit larger. Zoom in a little bit more. Okay. Throw this over here a little bit. All right, so what we're doing in our statistics for data analytics class is we're learning about JASP. We're going to now get into the set of statistical analyses called inferential statistics, and that is about hypothesis testing, and in particular, we're going to start the t-test. Now, you learned a little bit about inferential statistics already in the last module when we taught you about samples and populations and how we're going to use inferential statistics to infer something about the population from the sample. And basically, inferential statistics is also when you did some probability. You learned about probability. That's basically given some data or some information, what is the likelihood or probability that something is going to happen? That's basically making an inference. Well, we're going to get into more of that now, and we're going to get into hypothesis testing. So step one is to install new software on your Windows or Mac computer called JASP. So I'm opening up the website to show you what you're going to do. So this is the page for JASP. It is free. There's a lot of resources that you're welcome to use from here, and I encourage you to keep learning about this software. It's really, I'm finding this to be one of the most exciting new softwares out there that's free, that's built on R, which you've already learned. Think of JASP as like another R Studio, right? R Studio is an interface where we first had to install R, and then we installed R Studio, and then R Studio becomes the interface to run R. Well, JASP does it all collectively. It's going to, when you download it, click on download and pick how you want to install it on a Windows or a Mac. It's going to be a relatively big file, and it's going to take a while to install. So just be patient. What I want to say about the download is that you may get a prompt that says you need to update Java, or there's some other, like maybe a Visual Basic or something that needs to be installed. And it may say that you need to close certain applications in order for it to run. I suggest that you click the option, because it'll give you the option where you click do not close, a reboot will be required. So it's going to then go through the installation, and when it's done, you'll need to reboot your computer. Now, for me, I was surprised at how long the installation took. It took about 15 minutes, and I was concerned that it was frozen and it wasn't working, but it is slowly moving along. You see the bar, as it's working through. And I want you to just imagine what it's doing. It's first installing R, and then it's installing an R Studio type interface. And then once you reboot your computer, you will have installed on your computer, you will have JASP, right? It's a standalone application. It's also then going to be under your apps under J. And when you run it, there's no need to run R anymore or R Studio. It's all built in, and we're going to learn about that in this lecture. Okay, so I recommend now at this point, when you stop the video, install JASP, and then come back. Okay, welcome back. So now that you've installed JASP, let's go ahead and get into our lecture. In fact, let me make this even a little bit larger. Okay, so we are starting with inferential statistics, and the first inferential statistic we're learning is the t-test. A t-test is an inferential statistic used to determine whether there is a significant difference between the means of two groups. It helps infer conclusions about a population based on sample data. We've already done that in the last module. We learned about the difference between a sample and a population. Here's how it works and when it is used. It's based on hypothesis testing. So the t-test helps test one of two hypotheses or hypotheses. One is called the null hypothesis, or HO, which assumes that there is no significant difference between the means of two groups, right? Null means nothing, no hypothesis. And we have then H1, which is the alternative hypothesis. This assumes that there is a significant difference between the means. We're going to get into more of this in just a moment here. What is the t-test about? The t-test is going to generate a statistic called the t-statistic. The t-statistic compares the observed difference in sample means against the variation in all of the data. It considers both the size of the difference and the amount of variability based on the standard deviation. We also get from the t-test a p-value. The p-value from the t-test tells us whether the observed difference between the means is statistically significant. If the p-value is less than a predefined significance level, and we usually set that at 0.05, and that's referred to as the alpha level. So if we find that p is less than 0.05, we will reject the null hypothesis. We will reject HO, and we will therefore infer H1, that the difference between the groups is statistically significant. There are three different types of t-tests you're going to learn in this module and that you will be asked to complete and run and write up a little paragraph on using JASP. The one sample t-test, the independent two sample t-test, and the paired t-test. Okay. Okay. Just need to close my door. Okay, so we've done that piece. All right, so here are some of the assumptions that it's important for you to understand. The t-test is called a parametric test because it assumes the underlying population data fits specific distributions and is described by parameters like the mean and the standard deviation. These assumptions make the test more efficient, but limit its use to data that meet these criteria. So data should follow a normal distribution, and that's what we call parametric statistics. So it's the normal distribution, which we've been learning about. We're trying to assume that the data from our two groups are, the variance in the two groups is approximately equal. That's called equivariance. And that the samples are independent of each other, except when we do the paired, when they can be related. Okay. So coming back to the folder that we're working with, the JASP folder, the t-test, the ANOVA, the logistic regression, the linear regression, these are all examples of parametric inferential statistics. Chi-squared is an opportunity for us then to work with data where we're not concerned with the distribution at all. And in fact, then there are corollary statistical procedures to the t-test and to the ANOVA that are called non-parametric tests. And we'll see if we can get to those this semester, just as an example later on. All right, so some of the details of the t-test. The t is the actual test statistic, so there's going to be a value, and that value reflects the size of the difference relative to the variance in the data. And then we're also going to see something called DF, or degrees of freedom, in our results, and it's important to report that whenever we report the results of the t-test. Degrees of freedom is a parameter that impacts the shape of the t-distribution and determines the critical t-value required for statistical significance. Degrees of freedom represent the number of independent values or observations that are free to vary when estimating a statistical parameter. In the context of a t-test, the degrees of freedom are related to the sample sizes of the groups involved in the test. In simple terms, degree of freedom is the number of independent pieces of information used to estimate the variability of the data. Degrees of freedom affect the shape of the t-distribution. The t-distribution is wider and more spread out for smaller degrees of freedom, but as the degrees of freedom increases with larger sample sizes, the t-distribution approaches a normal distribution. So what do we mean by that? Well, as the sample size increases, we get closer and closer to the z, the z standard distribution that we already learned about. And remember that 95% level of significance, which referring to alpha equals 0.05, recall from the last lecture, that was z equals 1.96. So in very large samples, t of the t statistic, right, t equals 1.96, that would be right at p equals 0.05. Remember, what we're trying to do is we're trying to get the p-value to be less than the 0.05, which is the 95% level of significance. So we would be looking for a t statistic if we had a large sample size that was just greater than 1.96. We'll see this in some practical examples. It'll make sense. So in addition to reporting the t that we get, the degrees of freedom, the p-value, we also want to report Cohen's d, which is an estimate of the effect size. So in other words, just because something is statistically significant, just because we find a p-value less than 0.05, it may be a very, very small effect size, and it may not be that meaningful if, for example, Cohen's d is 0.2 or smaller. If Cohen's d is, let's say, around 0.5 to 0.8, we can say we have a medium effect size. And then if Cohen's d is greater than 0.8, and it can be even larger than 1, we have a large effect size. Now, Cohen's d actually refers to standard deviation. So Cohen's d is 1, then we're saying like this, the difference in group 1 versus the difference of the mean between the mean in group 1 versus the mean in group 2 is 1 standard deviation. If it's 0.8, we're saying it's 0.8 standard deviations different. How that translates to amount of variance that can be explained by the independent variable, that conforms to about 1% if it's small, about 6 to 7% in 2, and about 14% if it's large. Now, variance explained is going to become easier for you to understand in the module when we get to regression and correlation. But think about it like this. If we are trying to investigate if some independent variable has an effect on a dependent variable, and we can find that independent variable can explain about 14% or more of the change that we're seeing in the dependent variable, that's a lot of explanation. I mean, if you think about the stock market, if we could predict something at 14%, we're making a pretty good return on investment. So the more variance we can explain in our dependent variable by our independent variable, that's our goal. we would love to be able to explain 100% of why a dependent variable is changing because of the independent variable, but that's very, very rare. And in fact, you can see if we can even get to a place where we're explaining 14% or more, we're going to say that's a large effect. All right. So let's look at a hypothetical example. Suppose you want to test if a new drug, so that's the independent variable, if the new drug significantly lowers blood pressure compared to the placebo. So the independent variable is the drug. So we would use, one way we could do this is we could use an independent t-test, independent samples t-test to compare the average blood pressure between two groups, between a sample, randomly selected sample of participants who got a drug and an independent group of participants who got the placebo. So the test would help us infer whether there was any difference in blood pressure between the two groups due to chance, or whether it is in fact a statistically significant difference, and then we can infer, you know what, the drug does have an effect. All right. So the way I want you to think about this is start with the null hypothesis. What is our HO? Well, in this case, the null hypothesis would be that the mean blood pressure in the drug group is no different than the mean blood pressure in the placebo group. So we run our test, and if we find that the p-value that is reported is less than 0.05, then what we will do is we're going to reject this null hypothesis so that we can infer the alternative hypothesis. In this case, the alternative hypothesis is our study hypothesis. That's what we're looking to find out. We're looking to find out if a drug has an effect on blood pressure. So we would say, if we could reject HO, then we will infer H1, that there is a statistically significant difference between the groups, and therefore that the drug has an effect on blood pressure. And of course, then we would want to look at Cohen's d to see, well, was it a big effect on blood pressure? Was it a large effect, a medium effect, or a small effect? Right? So why don't we do some working examples and it will make sense. So you have JASP installed, and let's go ahead and work with the data that's in our t-test folder, this 2017 chr.csv data. And this is data from 2017. It's called the County Health Rankings data. You can look at the website. They have more current data if you want that you could download, or just grab 2017. And it's data from basically, it's data being reported by all of the different counties that represent the United States. So every state in the United States is made up of counties. Like in Michigan, we have Washtenaw County, we have Wayne County, Lawrence Tech, we're in Oakland County. So every county across the United States collected some data from a random sample of people in that county that responded to the survey. Okay, it's not everybody, but we can infer from this data what it's like in the United States. And also we can infer from the data what it might be like in any one particular state. Okay. Before we get into the example, let's get the data into JASP. Okay. Now, the first thing I want to teach you is we learned in R, R is fabulous, particularly in RStudio, for doing all sorts of data cleanup, right? We call it tidy data. And we don't have that same sort of luxury in JASP. JASP is a great statistical tool for running our inferential statistics. It's great for descriptive statistics. It does great visualizations. It's easy to make a report. It's easy to make journal quality outputs, publication quality outputs. It's not really a very good software for data cleaning deleting columns, deleting rows, manipulating the kinds of things that we could do in R through our studio. So let's leverage what we have in Google Drive, which is Google Sheets. Okay, now to get into Google Sheets, what we're going to need to do is take our CSV file and open it in, now it's, since I have not given any shared, since I haven't given you the opportunity to edit this folder, you're not going to be able to open up Google Sheets directly in this folder, but you can download the CSV file. All right, so let's go ahead and download the CSV file. Okay, so we've downloaded the CSV file. Well, now what you can do, if you, now that you have downloaded, is you can go ahead and go to using your Google Drive, go back to your Google Drive, to your Lawrence Tech account, and go ahead, and if you want, I suggest you create a new folder. And why don't we create, this will be our JASP assignments, or you can just call it JASP. Okay, so now we have a JASP folder. Okay, and we have edit this is your Google Drive, so you can do editing, you can do things with this folder. But one of the things that we can do is we can now, under new, we have access to the different tools in Google Drive, one of which is Google Sheets. So let's open up Google Sheets, and let's go ahead under File, let's import that file that we just downloaded. Okay, so we're going to click on Upload, and we're going to browse to that file that we just downloaded. It went to the download section. Here it is. And we're going to open it now in Google Sheets. So it's importing, and it's giving you some automatic, it's going to detect what the what the delimiter is, and it's going to convert text to numbers, dates, and formulas. So we'll import the data. All right, so now this looks just like Microsoft Excel, and it's a lot easier for us to delete columns and delete rows and change some column headers if we don't like it, and clean up some numbers and do some filtering. So I just want to take a moment to teach you this in Google Sheets. And this is really kind of like a primer on how you would use Microsoft Excel, because Microsoft Excel is very similar to Google Sheets. All right. We can give a name to this. Why don't we call this like our, this is our community health data, or if you want, you can just call this like our t-test. Now let's do the community health. It's the community health data, and this can be called like cleaned. Really doesn't matter, right? And it's in it's in our JASP folder. So in fact, if you come back, you could see now that Google Sheet is been in this new folder that you created. And remember, it's not a CSV file yet. It's a Google Sheets, but I'll teach you how once we're done cleaning, we'll go to File, and we will actually download it then as a CSV, which then we will open up in JASP. JASP doesn't open up Excel files. JASP opens up CSV or text files if you just have numbers. I really like working in CSV. All right, so like any data file, you've got an opportunity for there to be a column header row. So this row 1 would be imported into JASP as the actual column header names. So we've got county code, we have state, we have county, we have premature death value, poor or fair health value, adult smoking, adult obesity, physical activity, uninsured. These are pretty big, these are pretty long names. We could shorten them if we wanted to. We don't really need the word value. We have premature death. So we can see premature death. What does that mean? Well, in this, the county code 0 is really the average for the state. So in Alabama, the average number is 9,573 premature deaths. That's the average. So over here, poor or fair health, we don't really need the word value. So this is the percentage of people reporting poor or fair health. Adult smoking, this is the percentage of people reporting smoking. This is obesity, percentage of people reporting obesity. We actually don't even need the word adult, do we? This could just be smoking. This is obesity. This is physical inactivity, percentage of people reporting that they're not physically active. This is the percentage of people reporting that they're uninsured. All right. So now we just did a little quick editing so that when we do bring it into JASP, we just have some column headers that we didn't need to fix in JASP, but we could have fixed them in JASP as well. We don't need the second row because that's just an artifact of what was downloaded from the County Health's ranking website. So let's go ahead and delete, right click and do delete row. Okay. Now, the other thing here is you see here this, even though the actual number behind what we're seeing doesn't have a comma, it's 9573, we're seeing a comma. That is not, probably, it might not import well into JASP. It could come into JASP as 9.73. JASP may know how to read it as 9573, but let's just get rid of that comma. So let's highlight that column, or we could in fact highlight the whole data sheet, but let's highlight that comma. Let's go to format, number, custom number format. And let's just make sure that we're getting rid of the comma, right? So we got rid of the comma. So now we just have a whole number, which is great. So we've done that. Now what we want, one last thing that we want to do before we bring it in to JASP that I want to teach you. As I said, so every state has this 0 county code, and the 0 refers to the state average. Well, think about it. We want to do some analyses that reflect the data from the counties. If we also are adding in the average data from the state, we're kind of duplicating and we're skewing data by also adding in the average data from the state. So we want to really delete all the zeros. Well, we could just go to each 0 row and delete it and then go to the next, but that's going to take forever. Particularly, this is a long data file, right? If you sort down, you can see we've got the 3,186, if we think of the column header. Well, that's why it's 3,186. If we take away those 50 states, then we're left with 3,136, which I said is what we have, the 3,136 counties. So let's go ahead and use a filter and delete all the zeros. So what we'll do is we'll come under data and we're going to go create a filter. Create a filter. Oops, I did a mistake. So we can undo. I had this row highlighted. What we want to do when we create a filter is click this box here in the upper left. That's going to make sure that all of the columns are highlighted. Then we'll go to data and we'll go create a filter. And I just showed you, by the way, this arrow up here, that's where you can undo. So I'll undo that. Again, we're going to data, create a filters. Now, what does the filter mean? Well, it's click on the filter. It's showing you all of the values that make up that column. So let's start by clearing all of them. And then let's just click on 0 and click OK. So now what it's doing, it's filtering all of the rows, and all we're seeing are those rows that had county code as 0. So now we can highlight just those rows, and we can do the right click and we can delete those rows. So what we've basically done, we've cleaned this file. We've gotten rid of all of the county code 0. If we come back, this symbol says we had been filtered by this column, by this variable. If we come back here now and we say select all, and we do OK, now we have all of the data without the 0, right? In fact, if we go to the bottom, we can see, yep, 3,137 minus, right, the top header row gives us our 3,136. So we're ready to go. This is good to bring into JASP. We technically don't need the county code now anymore because we're not going to be doing any analysis on the county. So we can delete the column. We're really not going to be doing any analysis by the county name. So we can delete that column. And now we have the variables that you'll need for this example. So now that that's done, and it's in Google Sheets, if you ever wanted to come back weeks later and fix it, you could undo or go to different versions of that file. Now we want to actually download this as a CSV so that we can bring it into JASP, because JASP doesn't work with Google Sheets. So we'll click on this, and it was downloaded. Okay, you can click on this little folder here to show where did it download. Well, you can see it downloaded actually into your downloads folder. So if you wanted to bring that into your Google Drive folder so that you were keeping everything organized, you would just click on new file upload. So we're adding a file into our Google Drive folder, and we're going to the downloads section, and there's that file. And now we're just keeping our files organized. If you really want to be organized with Google Drive and you haven't done that yet, you can go to I believe here, and you can get Drive for desktop. And what that does is it will install an application on your computer, and then you will be able to access all of your files through folders rather than through the Google Drive. So I actually have 3 different accounts. So I actually have 3 different Google Drive locations. Right, so the one I'm working with now, I just created. There it is, JASP, and I could just work directly here by dragging files into here. I don't have to use the web interface of Google Drive. Okay, so now we're ready to work with JASP. So let's go ahead and open up JASP. And I'll teach you a little bit about JASP before we actually enter the data. So this is what JASP looks like. And this button here, so the button here is where we will work with data. We could type in data, or in a minute, we're going to open and import data. There are different preferences if you want to set different preferences as far as decimal places and things like that. Then you can see our analyses. Once we have data, we can do descriptive statistics, t-tests, ANOVA, etc. This button is showing different modules that are available, much like how in R, when we work with R, and then in RStudio, how we have to load different libraries before we can run analyses. Modules is kind of like that. One of these I'm going to use right now just to teach you something. They have one called Learn Stats. So if we click on that, then we can see that that module has been added. So why don't we look at, for example, normal distribution? Or we can look at p-values. All right. So here we have and why don't we change this to the t-distribution? Okay. So this is showing us a distribution, a plot, and we have alpha at 0.05. And because we have right here, the error rate is 5%, means alpha 0.05. And why don't we do degrees of freedom? Remember, degrees of freedom reflects the sample size. So let's say we have a very large sample. We have 1,000 degrees of freedom. And let's show the critical region for statistical significance. And you can see that cutoff value for where statistical significance will occur. So we're looking for p less than that. So it's this region here is going to be a t-value that's slightly larger than basically 1.96, right? Remember, we learned that with the z distribution, it's that 1.96. What if we have a very, very small sample size, meaning like a degrees of freedom of 10? Well, now you can see we need a t-value that's going to be somewhere greater than like 2.5 or something, or 2.3, okay? So I just wanted you to see that that is what's happening. I'm not going to use this module anymore. So in fact, what I'm going to do is I'm just going to turn it off. Okay, so we got rid of that module. Needless to say, though, there's a lot of really cool modules here that I'm starting to learn about. One of which is our console, which we're not going to get into, but you can, if you want to learn the intricacies between the JASP library and R code, you can actually do some coding with R right in this and run the analyses. But we're only going to do a little bit of that in this, but I'm going to teach you. So let's open up our data. We're going to do open computer. We're browsing then to where we have put those files. So I've put them in my drive, that JASP folder, and the reason why I'm able to see that folder is because I have Google Drive Sync here for the desktop. Now, if you didn't do that, you will need to go to downloads to open up that CSV file. Okay, I'm going to work directly from the Google Drive folder that I just created called JASP, and there's that file. So I'm going to click open, and it's importing it. And there we go. Oh, see, look, so that's the correct number. I tested this earlier, and with the comma, it actually imported it as 9.158. But you can see now, so that header row became a header. It wasn't row 1. And then if we scroll down, we see we have the 3,136 counties. So we're ready to do some analyses. Okay. So let's go back to the lecture and see what we're doing here. Now that we've done that, we've imported the data. Okay, so here's our example. Suppose you want to test if the amount of physical activity that a person has a significant effect on their obesity, right? So physical activity is the independent variable. Obesity is the dependent variable. So we're going to use an independent t-test, or an independent samples t-test. Often they just call it a t-test, but I want you to understand and be precise. The independent samples t-test to compare the average obesity between two groups that are independent from each other. One is a group that has low physical activity versus another group that has high physical inactivity. What if we wanted to create three groups? Low physical activity, medium amount of physical activity, high amount of physical activity. That's not the t-test. T-test is only when we have two that we're comparing two groups. The next module, which is ANOVA, that's when we can do more than two. And the groups, when they, in the world of statistics, groups is the letter J. So when J equals 2, it's a t-test. When J is greater than or equal to 2, you need an ANOVA. And if we wanted to work with all of the raw physical activity data and not turn it into two groups, which I'm going to teach you in a minute, that's where we get into the world of regression. Okay, so let's start with our, which I'll be teaching you in 2 lectures from now. Let's start with our null hypothesis. What's our null hypothesis? Well, the mean obesity in the low physical activity group equals the mean obesity in the high physical activity group. And if after we run the t-test, if we find that p is less than 0.05, we will reject the HO, and then we will infer our testable hypothesis, our alternative hypothesis that yes, physical activity has a significant effect on obesity. And then we'll look at Cohen's d to help us understand the magnitude of that effect. So let's just look at our data for a minute. So all of our data are continuous variables. We don't have any categorical, we haven't created any factors yet. We haven't taken physical activity and turned it into low and high. So we have to do that. We've got to create a new variable. We're going to add a computed column. We have to create a new variable that takes physical activity and tells us whether the particular physical activity is low or whether the physical inactivity is high. So how can we do that? Well, one of the easiest ways to do it, and one of the most common, is you do what's called a mean split. So what we could do is we could go to descriptive statistics, and we could find out what is the mean physical activity in all of the data. So you see here we have a nice descriptive statistics table. Well, the mean physical activity, inactivity, remember it's inactivity, is 0.2596. Right. So what we could do is, and then these little arrows here is how you get back to different windows. So I'm going to collapse the descriptive statistics window, or the analysis, the set of analyses windows. Can actually collapse this too up here with this arrow. That collapses that, still see the output. We're going to collapse this and go back to our data. We could also go to data, edit data at any time. So edit data gives us to our data window, and analyses brings us back to the opportunity of opening up over here on the right. I'm going to go back to the analyses and see our analyses. That's just how you navigate. This one gets rid of the analysis commands and just gives you the full results output. All right. So what we need to do is create a new variable, a factor variable, or a nominal categorical variable. That is, if any of these uninsured values are less than 2.596, we'll call them, or excuse me, any of these physical inactivity values are less than 0.2596, we'll call that low physical inactivity. And if it's greater than 0.2596, we'll call it high physical inactivity. Okay. So let's go ahead and show you how you can do that. So that's called a mean split. There's another type of split that people often do. We'll go back to the descriptives and go to statistics here. People also like to do a median split. That's pretty common, because median is actually then going to take your data and make two equal sized groups, 50%. In fact, why don't we do that? Let's do a median split. Okay. A median split of right at 0.258. So I'll teach you how to do that. So this will be a median split. And then we'll do descriptive statistics and find out if we get two groups that are approximately half of 3136. All right, so back to edit data. Click here to add a column. So now we have the opportunity of adding a column. And we're going to name it first. Why don't we call it, we'll call it the percent physical inactivity, right? So we're going to create a new variable and it's going to be either low or high percent physical inactivity. The type, so we'll hit enter. All right, now we have this column. Let's now start to tweak it. It's not going to be a scale. It's going to be a nominal variable. And let's compute it by using our code. So now here we can write code. Now I've given you some code here that you can work with. Why don't we start with this? This is the code. So copy that, and then you can paste that in here. This is the code if we were going to do a mean split, but we're going to do a median split, and we know that the value is 2.58. So the command is, this variable is going to be if else. Now we have to put the variable name in here, replace this. If, type it exactly as you see it, just like you learned in R. If physical inactivity is less than or equal, now we're going to get rid of all of this because we're just using a value, is less than or equal 0.258. We don't need this extra parentheses here because we weren't embedding the mean formula. This is just one formula. If else, it's basically saying if physical activity is less than or equal to 0.258, make it low, else make it high. And now we're going to click on converting types. And it just did it. So now we've done that, right? And we can see, yep, 0.286 is greater than 0.258, so it's high, otherwise it's low. So we've done that. Now, if we wanted to do the mean split, we would just go back to that formula that I showed you here. You can see again, see it's actually then you don't need to calculate the value of the mean. It's embedding it. There's the formula. It's going to do the mean of your variable name. Remember what we learned in R? We want to make sure to remove any missing, like basically ignore the missing. We don't want it to screw up our coding. And so that's what you would do if you wanted to do a mean split. Okay, mean and median split are the two common ways of creating a categorical variable from a continuous variable. So now we're basically done. We can close this. We have our new variable. Let's go back to analysis. Let's take a look at the descriptive statistics, for example. We have our physical activity. Let's see how close were we in getting. So now we're going to take our physical activity and split this physical activity into two groups. Pretty darn close, almost equal group sizes, right? Pretty cool. There's all sorts of stuff you could do with descriptive statistics. You can look at your distributions, all of these things that we did in R. We can display densities. We can output these images, save them as images, or what's really cool about this, folks, check this out. You could, for example, add a note if you wanted to add a note here and just start typing. You know, these are the distributions of the two groups. I'm not saying you need to do that for this assignment. I'm just showing you. And then check it out up here. Export your results to computer. Pick a spot. Why don't we go? We'll just go to downloads for a demonstration. You can output the whole thing as an HTML or as a PDF. So I will want you to output it as an HTML when you upload your assignment. Save it. It exported it. Now we'll come back to the downloads folder, open up that HTML. There's the entire output. No need to work with Microsoft Word, no need to organize figures, no need to work in Google Docs. It's a wonderful, and there's the little note we added. So it's kind of all embedded, and you can do it in PDF, and you can get very interesting outputs that are publishing ready. Okay, so let's do, now that we've done that, let's collapse this. Let's go ahead and actually, let's get rid of the descriptive statistics so that we have when we run our independent, we'll just have a clean output that you'll want to export. And again, what are we testing here? We're testing if the amount of physical activity has a significant effect on obesity. Okay, so we're going to do our t-test. You can see there's two types of tests. We're working in the classical, what's called the foundational frequentist parametric statistical tests. The independent samples, the paired samples, the one sample. There are Bayesian versions. Maybe we'll get to that towards the end of the semester. And so we're going to do the independent samples t-test. And now it's asking for a dependent variable. It's asking for our independent variable, which is called our grouping variable. Remember, it's only if J is 2. So it's got to be a categorical variable with 2, it's making 2 groups. And then you can see here, we can do the first test is called the student's t-test, and you'll see in a moment if there's a violation in that equality of variances, it's going to give you a note, and it's going to say you should use the Welch correction. And then if we really had a violation from normality, we could do the non-parametric equivalent of the independent samples t-test, which is called the Mann-Whitney, and we're not going to do that. We don't need to do that this semester, but once you do the t-test, you interpret them basically the same way, regardless of whether it's non-parametric or parametric. And then we would want to look at the effect size. We want to look at Cohen's d, and we want to look at the descriptive statistics, and we want to get a descriptive plot. We want a visualization. Okay, so what's our dependent variable? We're looking at obesity, percentage of obesity that was reported. And we want to see, is that predicted by amount of physical activity? Or in this case, we have data that you are physically inactive. Okay. So it runs all this for us. It gives us a figure. Now, first thing we want to do is let's look at the results here. So it's giving us this little, it's saying that we might have a violation of the equal variance assumption. So let's uncheck the student and check the Welsh, because the Welsh is a correction for any possible violation. All right. So what do we see, first of all? We see that the p-value is significantly lower than 0.05. It's like so low. It's like 10 to the negative 241. And the effect is super large. It's a huge effect. And what did we find in our group? Well, the amount of mean obesity for people that had low physical inactivity. What does it mean if you have low physical inactivity? It means you're active. Is a mean of about 28.5%, 28.6% of the people have obesity. In contrast, for those people that are in or that are also reporting high inactivity, right, which is low activity, they have significantly higher amounts of obesity. And here we see that visualization. And in fact, this effect is so large that it's got a Cohen's d above 1. It's so there's a 1.3 standard deviation difference between these two, which is a huge amount of difference. So you're basically done here. And what I would then do is I would go up here to this arrow and I would say add a note, and I would add a note. Probably don't need an introduction. I would just do your report down here. So an independent samples t-test was conducted to investigate if amount of physical activity has an effect on obesity. Results of the t-test suggest a strong effect, suggest there is, we can say large, a large effect of physical activity on obesity. And then you want to actually report the results. So I would do a colon, and then the way you report it is you do T and then parentheses your degrees of freedom equals, and then you report the T value, and then you report the P value, and then you report Cohen's d. So you do something like we've got T 3057.8. We can round it to 3058. So we would do T 303058 equals. There's that large T. Remember, we said, right, 1.96 is that place right at alpha equals 0.05. So we got 36.4. That's a huge T. 36. It doesn't matter, by the way, whether it's positive or negative. The positive and negative sign would just be, is one larger or smaller than the other? We don't really need that sign. We would describe that one was larger than the other. T, and then we would say, what, 36.42, comma, P. Now, in this case, P is less than 0.05, but you might as well make a point that the P was very, very low. So you could say P is less than 0.001. Now, what does that mean? Well, think about it for a second, and I'm going to just write this here so we can think about it. When P is at 0.05, that equals 95% level of significance. When P, let me do that one more time. When P is less than 0.05, we were saying that we have a 95% significance, 95% confidence, right? 95 times out of 100, we would find this. 5 times out of 100, we might find the null hypothesis. We might have made a mistake. That's really what P means. What if P is less than 0.01? Well, that's like saying 99% level of significance, or 99 times out of 100, we would find these results. 99 times out of 100, we would correctly reject the null hypothesis. 1% of the time, we might have made a mistake. Well, what is P less than 0.001? Well, 99.9% of the time, we're correctly rejecting the null hypothesis, and less than 0.1% of the time, we could have made a mistake. So these are the typical ways of reporting p-values. In some studies, if we want to be a little more liberal, we can. I've seen studies where people will do p less than 0.1, because that's still 90 times out of 100 is pretty good way of rejecting the null hypothesis. If you can reject the null hypothesis 90 times out of 100, that's pretty good. But what I want you to know, the standard is 95% level of significance. Very rare. You probably won't get a study to be fully accepted as significant result if p is not less than 0.05. Okay, so in this case, by reporting p is less than 0.001, we're able to really clarify why we also found that Cohen's d equals 1.3002. 1.3, so that was a large effect. And then you could maybe say, as shown in the figure above, we can just say, as shown in the figure, people with high physical inactivity are significantly likely to be people who also have high obesity. Got it? So you're done with that. Go back over to here, export the results, computer, export it. I'm going to put it in my JASP file on my drive as an HTML. I'm going to now change the name of this. I'm going to maybe call this, assignment A. Actually, you can do all of your assignment in just this whole output. Just do them all. There's one's independent samples. Next, I'm going to teach you the one sample. Next, I'm going to teach you the pair. You can just send the whole output. So it's just one file. All right. In fact, I'll just demonstrate that in a minute. Let's keep going then. All right. So we did that one. How about another? I gave another example. I don't think I really need to do it, but we can do it pretty fast. Why don't we look at the amount of health insurance and how it relates to health quality? So let's do that mean split, right? Grab the code for the mean split. That's the mean split, right? Let's do a mean split of health insurance, amount of health insurance. So we'll go ahead. If we were over here, we wanted to create our new variable, we'll go back to edit data, click on edit data up here, click on this plus here, so that we're going to create a new variable. Why don't we call this percent uninsured, because we know the percentage in each county. Let's now create a categorical variable, hit enter. Now we have that variable, define that it's a nominal variable. We're going to use R as the way of computing this variable. Type in that formula. So if uninsured, right, because we're using this column here, if uninsured is less than the mean of itself, then go and put in this column the word low. If not, put in this column the word high. Click on converting types. There we go. Now you'll see errors if it doesn't work. And let's say you wanted to just play around and practice. By all means, you can try the drag and drop method. I don't like the drag and drop method. I find it very difficult to understand how everything works. But here's all the different options. Like if you wanted to do that transformation like we learned in the last module, you'd create a new column, By the way, once you do a formula, it's really hard to do another formula. I found that it's easier to just create a new column, delete the column if you weren't happy with it. When it writes over itself, it kind of gets confused. All right. If you wanted to do that transformation, it would be log, you put, well, see, here's the, I don't even like the drag and drop. So then the R would just be simply, you would do, for example, log uninsured, right? That would be your R code, and you would run that, and that would create a log transformation. We're not doing that. You can't do more than one code in a line anyways. So we've done that. Oops, cancel. Uninsured is done. By the way, you know what we haven't done yet? We haven't saved this file. So be sure you save the file. Go over here, save as, computer, go to your folder, save it as a JASP file. You're now, next time you open it, everything's all done in JASP. You don't have to keep loading it up again. Let's do that. Then one more, click on analyses. We'll do another independent samples t-test of our example. We were now going to be looking at, I forgot what the question was. Health insurance has a significant effect on health quality. Okay, so the dependent variable is poor or fair health. That's health quality, right? Are people reporting poor health? And then we're looking at that as a function of whether you had insurance or not. We got that violation. Let's go to the Welsh test. We see a significant effect. Let's add in Cohen's D. Large, there's that large cone. Again, the negative doesn't matter. It's the absolute value. Here's our descriptive statistics. So the mean, we see the different means. And then we have our plots. So what do we got here, right? People with low uninsurance, which is another way of saying they have insurance, they're reporting little poor health. So they're reporting good health. Whereas those counties where there's high amount of uninsurance, there's high amount of people reporting poor health. Okay, let's go on to the next example. Suppose you wanted, so now we're going to go, I purposely started with the independent samples to teach you because it's a little bit easier to think of the null hypothesis when we think of means between two groups. Let's now get into a one sample t-test. Suppose you want to test if the amount of health insurance in Michigan is different from the national average. So we would use a one sample t-test to compare the mean health insurance Michigan to the national mean. So now we're still thinking of it as two groups, but in this case, the two groups are the one group that we're looking, the value of one that we want to test against just a value. We're thinking of the other group as just a value. So in this case, the null hypothesis is that the mean amount of insurance in Michigan, or we just did the uninsured, the mean percentage of uninsured equals the mean percentage of uninsured in the USA. If we find the P is less than 0.05, we reject this and we infer that, well, the mean in Michigan is not equal to the mean in the USA. So it's different. And then we would just report what it is and we would visualize that. So let's go ahead and do that. Okay, so there's a couple things I need to teach you before we can do that. Let's go back to descriptives and let's find out what is the mean amount of, so we don't need these groups anymore because we're going to be doing something slightly different now. So let's find out what is the mean amount of insurance in the United States. Okay, so the mean in the United States is 14.4%, 0.144. Right, so we're estimating that 14.4% of people in the United States do not have insurance. They're uninsured. All right, what's the flip side of that? 95.6% do have insurance. Or excuse me, 85 do have insurance. That's pretty good. Pretty good. I thought it was going to be lower. Not bad. Of course, I'm sure there's a bunch of variability. And in fact, we could look at that variability if we want by doing a distribution plot and looking at the density. Yeah, I mean, so there's there's a lot of variability, right? So that's our mean, but some states have as high as almost what, 60, almost 60% of the people in their state do not have health insurance. Excuse me, almost 40% of the people in some states do not have health insurance. So almost half the people in some counties in America, that's a lot of people that don't have health insurance. All right, anyways, so we just did that. So we've got this number that we wrote down. Let's go ahead and delete this. And now what we need to do is, if we wanted to do a one sample t-test of just Michigan, we have to make sure that what we're analyzing, what our data set contains, is just the Michigan data. Well, it doesn't right now, right? The data contains all of the states. So let's set up a filter, show filter. And here's where we will do a drag and drop. And let's create a filter, a pass-through filter, that's only going to pass through whatever we tell it to pass through. So let's click on state. Let's say only pass through if the state equals, and then these three dots, will click on it, and we'll type in exactly the logic. It's got to be exactly the value. If the state equals Michigan, now we apply the pass-through filter. Actually, we could do it as an R code. There's the R code. So right in this case, I find it easier to just do the drag and drop. So what did it do? Like, all of the states that are not Michigan are blanked out. So the analyses, when it's conducted, is only going to conduct it on the rows, on these rows that are Michigan. Right, so good. That filter is good. Now we're going to go to analyses, and we're going to go back to t-tests, one sample t-test. And now we're going to say, let's look at the uninsured. And right now, it's testing it against 0. We don't want to test it against 0. We want to test it against the mean in the United States, which is 0.144. All right, click, and we can see we have a significant effect. And it actually it gives us the interpretation. So it's saying the mean in Michigan is different from 0.144. Well, let's put that effect size in over here like we did before, Cohen's D. It's a large effect. Let's go ahead and actually find out what it was. Oh, in Michigan, it was less than. So, right, only 11% of people in Michigan are uninsured. And then we can visualize it with our descriptive plots. So it's showing us the test line, and we can see Michigan has less amount of uninsured. So Michigan has more people that are insured in Michigan. So that was our one sample test. So that was done. And then you can, again, remember, come up here, add the note, write your interpretation, right? Write your interpretation. Results find that there are significantly more insured people in Michigan versus the nation. And then how do we report that? Well, we say T, do that column, we'll go T with 83, excuse me, T with 82. You can see then degrees of freedom for one sample is just your sample size minus 1. T82 equals 16.68. P, again, we have that very low P, so we might as well say 0.001. Cohen's D equals 1.83. Okay, so that's done. And then finally, Now, here's the thing though, since so actually you'll do two outputs. One output, because you're going to be working with this data set for your first and second, your independent samples question and your one samples t-test question for the assignment. But for the paired samples, it's different data. So whenever you open up new data, it creates a new session. So you can't combine the outputs. So at this point, then, once you've done your two, do your output, export it, like I showed you, pick a folder, export it as an HTML file, maybe call this, questions, t-test questions 1 and 2. Right, and then you'll upload that. You'll be uploading 2 files into Canvas. This will be one of them. I actually downloaded it into the JASP folder. The t-test. There it is. So there's your answer to the independent samples and the one samples t-test. Well, now we have to get to the paired samples t-test, which is going to be a different data file. Let me give you an example with a data file for an example. So suppose you want to test if the lunar cycle has an effect on disruptive behaviors in dementia patients. Your data needs to be the same patient measured during different lunar cycles, full moon versus other moon. So in this case, each row corresponds to one participant and columns are the repeated measures. So now we're getting into a language called repeated measures. And that's what the pair means. It's like variables are paired together and rows correspond to people. In this case, then, the null hypothesis is that the mean disruptive behaviors when it was a full moon equals the mean disruptive behaviors when it was another lunar cycle. And if the p is less than 0.05, we reject the null hypothesis and we infer the alternative hypothesis that the lunar cycle does have an effect on disruptive behaviors. So this we don't need to clean in Google Sheets. Let's just go ahead. So now we're done with this. You can save this. And when you reopen this, it's going to open up your data and all your analyses. So it's all now ready for you to do your assignment. You can remember to turn off your filter for getting all the data back. How do you turn off the filter? Just throw it into the trash. Because even if you close the filter window, let me see, does closing the filter window? No, even if you close the filter window, the filter is still in effect. And you can see here, this symbol is saying the filter is in effect. Now, to turn it off, double click the trash bin, and now it turned up, the filter has been cleared. And now you can see that there's nothing is filtered and you have all of your data. Okay. Let's save that. All right. Now we want to open new data. I'm going into my JASP folder. Oh, sorry. I've been teaching you, we have to go to the folder. We need to download the data, right? My bad. Let's download the data that is in the teaching example. So this is the moon data. Your assignment, you'll use real estate. So it's however I teach you to do moon integration, you'll be able to do it with the real estate data. So let's download this moon data. All right, so I downloaded it to my downloads folder. Let me put that back in the folder that I've been working on, which is my JASP folder. Throw that in here. There's the moon data. And now we will go ahead and open that moon data in JASP. There's the moon data. Open it up. See, it starts a whole new session. So you'd get a whole new output, and that's why you can't combine data frames into one output. Unlike R can do that. Okay, so here we have the same people measured at two different time periods. This is disruptive behaviors for participant one when it was a full moon versus disruptive behavior for patient one when it was an other moon. And this is very simply a paired samples t-test. And it's what you're doing is there's no longer an independent variable. You're putting in the pairs that you're testing, and you can only test one pair at a time. So if you had different measurements, like if you had full moon, half moon, quarter moon, you can only do one set of pairs at a time. In this case, we only have full moon versus other moon. So full moon is added, and see, it's asking for what are you testing that against in the same person? Well, in the same person now, we're also testing other moons. And this is the non-parametric equivalent called the Wilcoxon signed rank. And we can see we have a statistical difference. Let's also get Cohen's D. Let's also understand what those means were. We see there's big difference in the means. Cohen's D is very large, and then we can plot it. And there we go, right? So when it's a full moon, there's significantly more disruptive behaviors, right? An average of 3.02 versus when it's another cycle. So do the same thing as I showed you, add your note, type it out, give me a interpretation, please. Actually, it looks like you can export here. Oh, so that's interesting. I didn't know that. So actually, I guess you don't need to necessarily go to export. So let's try that again over here. Let's open up the session we just did on this one. On the county health data. And so, yeah, we could take this whole results up here and we could export it. There you go. So, right, still have the option. You can see there's all sorts of things you'll be learning. You can also, if you want, you can show what the syntax was for all of these, etc. So I think this has been a good overview as far as, so here's our different sessions. Here's our moon. Again, how I would interpret this is I would simply say, I think, can we move these boxes? I don't know if we can, oh, maybe. I don't know if we can move these boxes. No. You know, results of a paired samples t-test found disruptive behaviors in a sample of, usually good to give more details, so I didn't really do that before, so I apologize. We might want to say results of a paired samples t-test in a sample of 15 dementia patients found significantly. If you find statistical significance, that's when you can use the word significantly. What if p-value is greater than 0.05? You would just say did not find significant difference, or found there was no difference, something like that. Found significantly more disruptive behaviors during the full moon than other moon cycles. All right. So what we would say, T with 14 degrees of freedom equals 6.45. P is less than 0.001. What is it actually? Well, it's 5 zeros, right? So it's technically 0.0001. No, 0.00. Actually, if you really wanted to report it, you could report P equals 0.1234151. It's the whole number. Cohen's D equals 1.67, right? And if you really wanted to have fun, which you have to do in journal articles, you'd say specifically during moon cycles, there was a mean of 3.02 disruptive behaviors, right? We got that from our descriptive statistics down here versus a mean of 0.59 disruptive behaviors during other lunar cycles. All right, done. Export our results. This will then be T test question 3. Done. Import, go to where that was downloaded. Import that into Canvas, and there's your output. It's all nice and clean. It's really professional looking, great table. You don't have to do any formatting, don't have to do any column things. Just type out your interpretation. Give us some details, have some fun, write it out. Okay. And then I think what we're starting to do is we're going to start having you actually, like I'm doing now, record yourself in Zoom presenting these results, because we want you to start practicing presenting results to help build up those professional skills. All right, good luck. Let us know if you have any questions. As we move on to other modules, now that you know JASP, we're just going to jump right into JASP and start teaching you these. Okay, take care.